Hello and welcome to this video demo of Eclipse Freebird Tools. Eclipse Freebird Tools does three primary things. First, it imports all the artifacts from the Bird Access database, such as cubes, variables, domains, etc. Then it creates a simple lineage model and also then an advanced lineage model to show the dependencies between different artifacts such as data points and input variables. So let's first look at the imported files. So the files are imported from the Access database into an XML file structure which is compatible with a modeling standard called EMOF, or Essential Meta Object Framework. So here we can look at the variables. And let us find the variable called country of residence. If we click on that, we can see in the bottom right hand corner the details such as the code, the domain ID and the variable ID. Now we can right click on that and show a visual representation. This visual representation is very simple. It's basically just saying that the country of residence has a domain geographical area. However, when we click on geographical area, it takes us to the domain in the left hand panel, and we can see in the bottom right we've got the details of the domain, such as its data type here being a string, its code being like this. And when we're at the domain, we can create a visual representation of the domain. This will take a few seconds, but this shows us all the different members of the domain, and then we can click on a member such as Ulrich, and we see again in the bottom right the code and the different IDs and the different details associated with that member. The second thing we show is a simple lineage model, and this is showing only the lineage and dependencies between transformations and input layer cubes. Now, to show this effectively, we've created a tiny version of Bird which has just 3 input layer cubes, I think 5 transformations, and the input cubes only have a few columns each, and that allows us to show the lineage model easily. So here's the visualization. So we can see we have an input layer. The input layer cubes here are in yellow. We have one called loans, one called counterparty, and one called rating. And the transformations are in red. So this one is called aggregate loans, and it aggregates loans by counterparty. This one is called aggregate loans and counterparties. So this joins the counterparty information to the aggregated loans. The third transformation is called loans, counterparties and ratings, which joins that previous information to the rating information, also the rating of the counterparty. And this last transformation is called enriched exposures. It adds one column to the dataset which says how much of the aggregate loan is AAA. And then in green we have 3 data points. First, total US notional, so it's a data point where the country is US and the field that we're interested in is notional. Next, notional of US AAA, so the field we're showing there is the amount of AAA for the country US. And the third data point is total JP market value, where the country is JP and it's showing the total market value of all the loans for the country JP, Japan. Now we can show a bit more information in this diagram. So this shows us here that the cube loans has a schema, and we can show a visualization of that schema, basically which columns, which variables are in that input layer cube. We see it's got 3, market value, notional amount, and the entity identifier. We can see that this transformation aggregate loans is associated with logic, which is a group by logic. And we can actually, if we look at the bottom right hand corner, we can see the VTL behind that transformation. Then we can see that this transformation was a join transformation. This transformation, loans, counterparty and ratings, was also a join transformation. This transformation, enriched exposures, was a enrichment transformation, which added a column to the data set. So that covers the simplified lineage model. Now let us have a look at the advanced lineage model. Now, if you're familiar with VTL, you will know that the structure of the data sets created by the VTL transformations can be determined from the transformation and the structure of the input data sets. So we're showing here the structure which we already knew of the input cube called loans, and then we have worked out the structure of each of the data sets which are produced by the transformations. But we also saw the dependencies here. So in yellow, we see this dependency is showing that the whole data set called aggregate loans, the result of the aggregate loans transformation, is dependent on the column entity entity LEI. This is because if that column didn't exist, there would be no way to do a group by on that column. So all columns can be said to have a dependency. All columns of aggregate loans can be said to have a dependency on entity LEI. And in red we show the more obvious dependencies. Market value came from market value. Actually we know, we can follow on the left hand side how that, some more information about the dependency. It was actually a sum of loans ECB to market value. We saw that the notional amount came from notional amounts, LEI came from LEI. Here again, from this transformation, we see that in yellow that the whole table is dependent on LEI in both the counterparty source input cube and the aggregate loans transformation. This is because these are the two fields that were joined together in the join, so they must be present. So the whole data set has a dependency on those. However, notional amount just came from notional amount after the join is done. So that's a more simple dependency. And this goes all the way down to the data points at the end here. Now, this is not just a simple audit trail. This is very advanced and intelligent. It is executable and divisible. We can divide it into smaller parts, and the smaller parts are also executable. So that's best shown with an example. Let's see if we can get this full screen again. Excellent. Okay. Let's try again. So here's the full lineage model. And here we've grayed out all the things that are not actually are not dependencies of the data point total JP market value. Let's compare the two again. Oh. Yeah, so we can see here we basically removed anything that is not dependent on that is not a dependency of this data point. And this tells us some information, very useful information. One, that the field notional value in loans was never actually used to calculate total JP market value. Credit rating was never used, and so if in the future that's removed from the data model, credit rating agency, it would have we know that it would have no effect on the data point total JP market value. Now, this sub-part of the lineage model and the entire lineage model are executable, and they don't just execute to produce a number, they execute to provide a full data lineage model. So we not only have the number, but we can trace back exactly how that number was calculated in a format that should be very familiar to users of Excel. So let's look at the data lineage model produced by the execution of this sub-part of the lineage model. Here we say we provided some information, some sample input information for this input layer. So loans, we had a market value of 5,000 for Mitsuho, another 9,000 for Mitsuho, 15,000 for Citibank. And we provide some counterparty and rating information, and we calculated total JP market value here. So here we've got a subset of things. We threw away lots of information that we didn't need. So we didn't even provide notional value for the loans, because if we look at the attribute lineage model, we see that notional amount is not actually needed. It's not a column or a variable that data point is dependent upon. We can also show the dependencies between each of these numbers, so going all the way to the data point value and through the intermediate results. And it's a little bit messy in this first visual representation, but we can see, for example, that this number 14,000, it came from that 9,000 and that 5,000. We can actually see the calculation, I suppose. If we go click on 14,000, we can see on the left is an aggregate function which was sum of the two different cells here. So this is very much like an Excel spreadsheet where you have lines between formula showing the results of calculations performed on cells, and it's same conceptually the arrows between these cells and the arrows that you can see in an Excel spreadsheet. So that's us seeing that our attribute lineage model is both executable and divisible, and the divided parts are themselves executable, and the division allows us to, when we're writing a test or focusing on one task, throw away hundreds of pieces of information that we have no interest in at all. So in the full bird, we have hundreds of columns in input layers, and this allows us to focus just on the ones that we are interested in for the task at hand. Now, another interesting thing about this advanced lineage model is that we've seen that we can divide it into parts, and we call these parts a trail, as a sub-part, a trail through the logic of bird. But conceptually, we can think of the entirety of bird as a superposition of all these trails, one per data point. And that means that we can actually, between two versions of bird, compare the difference between all those trails, and this will allow us to give us good insight into change management of which logic for data points has changed and which input fields are now used in a different way, giving us a lot more insight into the changes that have happened. So that concludes our quick demo of Eclipse Freebird tools. I hope you have enjoyed watching.